All right. Get into presentation mode. Okay. Um, on this new unit, we've already started this first objective looking at and being able to build graphs. But what we're going to do is we are going to use and understand the metric system better and its prefixes. We're going to take a look at derived units and how we get more than just our base units. We're going to look at expressing scientific notation. All right, so those are going to be the three that we're going to take a look at today. And then when we get into next week, we're going to take a look at something called significant figures, precision, dimensional analysis, and a bunch of fun stuff that I hope you like. So I want you to take a look at this. Take a look at this list, the reds versus the blues, right? What is the difference in the groups of statements, right? So if you look at the reds, what do they have in common and how are they different from the blues? And I'm guessing most of you can pick this up right away, okay? The reds are what we would call qualitative and the blues are what we would call quantitative, right? And when we look, that makes sense based on these definitions, right? Qualitative involves the senses, right? It involves observations with your senses, where quantitative has a direct relationship with the number. So when we go back and we look at that first slide, right, there's no numbers up here. There's blue, there's pink, there's tall. Like obviously you could measure a building, but just this statement is more of a qualitative statement than a quantitative statement. It takes me a long time to ride my bike to the store. Obviously, we could time it and we could put a number associated with it, but really long is a qualitative observation, a qualitative set of data. Okay, so when you look at that red group, those are qualitative. Where quantitative, the river is 31.5 meters deep. All right, we could say that water is really deep, but the really deep would be a qualitative, where quantitative, like we are getting a number. We are getting something very specific. Cheese costs $4 per pound. It's 75 degrees Fahrenheit outside, right? Those all directly involve something that we measure. So when we take a look at this, this involves the senses. Not that we don't see these, not that we can't, interact with these the same way, but when you take a look at qualitative, when you're giving me qualitative observations, because that's normally what we're going to call them in a lab, that's what they are. They're anything that you can tell me with your eyes, your ears, your nose, right? Your touch. And quantitative are usually the things that we are going to write down as a number, that data, the things that we're going to call data. So that's another way to put it. So it's going to be important that you understand those two terms. So when I talk about them, you'll know them from here on out and what types of information I'm looking for. Okay. So the different types of information. So we have this thing called the SI system. Okay. The SI system is this guy over here. And you can probably look at some of that and know some of them are. And we're going to take a look at that in the future. But what does SI stand for? Okay. It stands for System International. Okay, System International. So when you're thinking about that, why do we have the System International? Well, before we answer that, it all started in the 1960s. Okay, the 1960s is a time of growth of the entire world, right? And that's really why this was created. As the world is starting to grow, and there's more and more scientists doing more and more difficult things, harder and harder research, as commerce, right? As we start to trade more and more with other countries and get things in. We needed some standard system worldwide that people could follow, right? Because there has been many accidents where this hasn't been followed, and we'll kind of talk about some of those in our live session, right? Of where this could potentially be a problem. So why did they create it? Just for this, we need to work together, right? Worldwide, even especially now. I mean, obviously, we're a ways away from the 1960s, but we need to work together. You might have a job someday where you're working with somebody in another country, maybe a different language, and language is hard enough. But what science tried to do is we tried to make a common language that everybody can use worldwide. All right, and you already know parts and pieces of this, but that's where this guy comes in. Different types of measurements that we got to take. We have a standard form. If you're going to create a a document or something that's going to go worldwide, you need to use one of these standard forms. Obviously, we use things that other than these that we're going to talk about, but the need is there when we start doing things worldwide. All right. So those things we just looked at on the last slide, those were called our base units. So these are physical standards of measurement, right? These are things that are quantitative, and we're able to use some instrument, some device in order to measure them out, right? And there's only 7 of them. But think of how many things that you know that you can measure, or different measurements or different numbers that you've ever seen or heard or taken in your life. How can there only be 7 base units, right? Doesn't there have to be more? Well, there is, and we're going to talk about that in a little bit. But basically, it comes into this idea of being derived, right? We can start with these 7 units, and especially if you've taken or are going to take physics, right? You start with the basic equation, and you take that equation and you morph it into what you need, right? That's really what mathematics is. That's what science is taking what we have and making it even better by making it more difficult, making it more challenging. But the necessity is there to make our lives more efficient, to make our lives better, right? So maybe we're taking the pH of something. We have the red and blue pH paper where we can tell if it's an acid or base, but, we have a device that could measure the very specific pH to, the 10th or the 100th of that degree, right? A measuring tape, right? So whether we're designing a house, we're, taking measurements inside our classroom, right? Just getting that unit of length is a good one. Or just, some of these, measuring cups and things. And this actually isn't even a base unit, right? Why would this not be a base unit? Isn't a volume something very, very basic? So shouldn't it be a base unit? We're going to talk about that. All right, so our base units are the 7 units where everything could come from. And so that's what this guy is, right? So we have mass, which we record in kilograms, okay? And its abbreviation. Length, the SI unit is meter, is just a lowercase m. Time, we have second, which is an S. Don't worry about that A. But SEC or sec we cannot use. Temperature is in Kelvin, right? We won't need this too much. Like in class, for the most part, we're going to be able to use Celsius. But there will be a point at this year where Kelvin is going to be a necessity, but I'll let you know when that is. And the amount of a substance we call a mole, right? A mole is going to be new to you. You've probably heard of Kelvin before. You've definitely heard of the first 3 before, but a mole is something new to chemistry because it's a chemistry term. When we want to talk about the particles, when we want to talk about the substances that are smaller than an eye can see, we start with that unit. That's called a mole. So we'll have a whole unit on that when the year gets going. All right. Electricity, ampere. Probably heard about that. And luminosity is candela. You can look at the side of a light bulb box and you can see candela right on there. Okay. But the ones we want to know that we need to use in this class are going to be those first 5. We're not going to use amperes very much. We'll use some electricity, but we won't need to actually use that unit in candela. We won't need either, right? So make sure you have these, make sure you know their abbreviation because they are going to be frequent, and I need to know that you know how to use them and what they are, right? Everything else can be derived from those. All right, so besides just the base unit, right? That's this guy right here, right? So we can put a second in here, we can put a meter in here, we can put a gram in here, right? That's that base unit. And you've had this before, right? This is your kilo, hecta, deca, our base unit, deci, centi, milli, right? What I want you to know is I want you to know all of these in CITS, right? So we want to know mega, right, on the large side. And we want to know micro and nano and pico. And so for micro, if we're typing in, we're just going to use a U. Really, it's an italicized M with a little tail on it, but that's hard to do. And just seeing an italicized M isn't usually that useful. So that's why this one sounds weird, micro, nano, pico. Okay. Something I want you to write in your notes is this, right? And we'll probably do this in the live session too, but making some markings right here. Okay, between mega and kilo and between milli and micro. Okay, because there's a distinction between what's going on in here and what happens outside of this. Okay, and so basically everything in the box, and the reason the metric system is so convenient is it uses tens, right? It uses tens, and it's nice and convenient because of that. Every jump is a jump of 10, and that's what we see up here, right? From deca to hecta is a multiplication of 10. From hecta to kilo is a multiplication of 10. We can do the math in our head. That's why it's nice. The thing we struggle with in school is the fact that we just don't understand, like, what is a gram? How much is a gram? What is a decagram? What is a kilogram? Like, we don't understand what they are because we use other units. Like, if I ask you to get me a pound of something, you could probably get close. Where if I ask you to get me a gram of something, like, I don't know. And that's why we struggle with it. But mathematically, it is so much easier. Okay. So from kilo to milli, these are all jumps of 10. So basically the difference between milli and a kilo is a million, right? Because it's 6 jumps. Now, when we get outside of this bracket, right, they are jumps of 1,000. So to go from kilo to mega is 1,000 times bigger, right? To go from milli to micro, it's also 1,000 times smaller, right? So here's 1,000. Now, every jump, I don't care, because in chemistry we deal with small things. We don't deal with big things. So I don't care that you know these things that are bigger. You can probably guess if this is a kilo and this is a mega. Can you guess what this guy is going to be over here? Bet you can. All right, but over here we do have really small things. So we have milli, right? And we have micro, and we have nano, and we have pico. So this is 1,000 times smaller, and another 1,000 times smaller, right? So you get on this end and you start getting really, really small, really, really fast. Okay. Now, for most of our lives, we live in this region, but every once in a while, we need to get really, really big, or we need to get really, really small, and we don't want to write all the zeros in. And so we have these prefixes that are going to help us out with that. Okay. So we can have acronyms like this, and I'm actually going to make you an acronym. Here's one from kilo to milli. It's King Henry died drinking chocolate milk, or by, I like to put in there to remember that base unit. So all of these are a jump of 10, and we're going to talk about that in a little bit. But this is a good one to kind of remember those main base units, and you probably heard that before. King Henry died drinking chocolate milk. All right, just as a way to look at that. So here is kind of the whole system of prefixes. We're not going to need all of these things, but you can see we have our kilo to our milli, right? All jumps of 10. But then when we get past that, we get mega. How many of you guessed giga was after mega? And you actually know this one, tera. Most of our computers are starting to get into the terabytes. But guess what? We can keep on going all the way up to zeta, iota, right? And all the way down. So we're going to stop here at pico. But there are Fermis that, depending on what you do and who you are, you might need to use, all right? Different units. So this is a laundry list. But basically, we want to know from mega all the way down to pico, which we had on the last slide. I just want to show you that there is definitely more. So we have our derived units, right? So we have a couple more topics, derived units. So not all units can be created by base units. So these derived units are by using combinations or parts of those, right? So an easy one is area, right? We have the unit of meter, right? And we put two of them together and we create an area, right? Just like you've always done. So length, or length width, we get an area. Length width, multiplied a few times, we get an area, right? So you've dealt with derived units before, but what we want to realize is that they start with a base unit, right? They're starting at the very basics of something, and then we're making them bigger. We're building on them. The next one we want to be able to do is a derived unit of volume, right? And we said this way at the beginning, like volume is very basic. We use volumes all the time, gallons, cups, right? Liters, meters, milliliters. Well, it's actually a derived unit, because when you look at just this cube, right, when we think of a solid object, like we have length and we have width and we have height, and all of those things become or originated as this base unit of meter. Okay, and we can make them bigger and we can make them smaller and we can multiply them together, right? And so that's what we do to find a volume. We take length times width times height, right, to get this. Or in the case of our classroom, so we have the centimeters cubed or meters cubed or whatever we want as a solid. In our classroom, lots of times we'll use milliliters, right? If you've come in and you've done a lab so far, that's what you've got. So one of the conversions I want you to know is this one. Oops, go backwards. No, is this guy right here. Maybe I'll get my pointer out. This is definitely something you need to remember. So we have this point between solid and liquids where they're always the same. Okay, 1 centimeter cubed, one of these little blocks right up here is equal to, well, I guess these are meters, but we have blocks like this in class. One of those would be equal to a milliliter worth of a liquid. Okay, so when we talk about these derived units, it gets a little bit complex, right? So I want you to do it, and we'll talk about this in class. If you had 10 centimeters cubed, how many liters is that? Okay, how many liters would 10 centimeters cubed be? And also, if you had 1 meter cubed, how many liters would that be? Okay, I want you to try those out. I'm going to give you some time to do that, and just give me your best guess or what you think it is in the Edpuzzle, and then we will talk about it in class and see how close we got. All right. So the last derived unit we're going to talk about now is density, because one of the next labs we do, we're going to deal with density. So when we take a look at this guy, it is now all of a sudden we're taking mass. We haven't talked about mass, but we're taking mass, which is in kilograms, right? Or grams in our case. And we're going to do it with another derived unit of volume. So this is like a double derived unit. Okay. And again, you've done with it before. It's mass divided by volume, a base unit and a derived unit, just to make a more complex derived unit. And that's what we're talking about, right? And so we have this thermometer over here. So this is like a super derived unit, because we have temperature in here, but we also have density in here. And we have, this is called a Galilean thermometer. I have one in the back of my room if you ever come in and want to check it out. But it's pretty cool. It records temperature based on the density of those bulbs in the water inside. All right, so we have, our equation, density equals mass divided by volume. We're good, and I'll give you a second to solve this problem to see where our math skills are at, and we'll talk about this when we come into class, right? So what is a mass of copper wire with a density of 8.63 grams per centimeter cubed if it had a volume of 36 centimeters cubed, right? You should be able to solve that pretty simple, but we'll make sure we have that baseline. All right. So getting to our last couple topics, scientific notation. Again, you should be good at this, but it always strikes me that we don't always teach the rules the same way. All right, so when it comes to scientific notation, so taking a really big number and making it look more manageable, right? So one place value in front of the decimal, that's the first rule, right? So when you're giving me something in scientific notation, there should always be a significant digit, and we'll talk about that, in front of the decimal. That means a 1 through a 9, right? So every number should look something like this. The lowest you can have is 1.0. The highest you can have is 9.9. Other than that, you've done the rules wrong, right? The next thing is you must show all significant numbers. And that doesn't mean everything your calculator tells you, but I'll talk about that at a later point when we get to it, okay? So we're going to call these sig figs, or significant digits. Some of you might have heard about that in 9th grade, but some of you may not have. And the last thing is we always want to use this if we have a number bigger than 1,000 or less than 1,000. So basically, if you have 4 digits or more, we want to see in scientific notation, because it just makes it easier. So again, I want you to try out these two problems quickly in the Edpuzzle and tell me what you come up with. Okay, and then we'll talk about it in class to make sure we're all on the same page. All right. Last two things. Mental math. Okay, if you just added these two numbers up, right, you get 11.71 times 10 to the what, right? And so the idea is here, if you're going to add and subtract mentally, you need to have or make sure that exponents are the same. So you can change either one of these. It doesn't really matter, okay? If you change this one to a 2, that's going to make this number 63.6 instead of 6.36. Or you could take this one and turn it into a 3, and that's going to turn this number into 0.535. It doesn't really matter. It might in the long run with your final answer if it doesn't come out in the right scientific notation. But to get the math right is not a problem. But I just want you to do this. You're always going to have a calculator to do this. But to be able to kind of quickly think about what an answer should be before you rely too much on your calculator, because you implicitly rely on your calculator when it comes to math. And sometimes you got to be smarter than your calculator, because you're the one that typed in the numbers. And so I want you to understand, not that you have to show me your math, but I want you to understand what the answer should be close to before you do that. So I'm going to probably have you practice some of these. So when you try this one out, you can do either version of it and come up with the right answer either way, okay? And put that into scientific notation properly, and we'll talk about it. All right, and the last one, this is really the most useful, and then we're done for today, is when you multiply or add exponents, okay? Or when you multiply or divide exponents, sorry. When you multiply exponents, you just add them up. So you can do this math out here, and again, you've learned this before. So you have 3.45 times 4.1, right? You can put that in your calculator, but just quickly, and this is really what I want you to do, not that we shouldn't be able to get, somewhere around 13 in our head with that, but what you should understand is when you put in your calculator, you should have times 10 to the 8th, or 10 to the 9th, or 10 to the 7th, depending on the problem, but it should be within one standard deviation of 8, because those add up to 8. Same thing down here. If you did this one, and you came up with a number that didn't get you somewhere around 10 to the negative 3rd, you would be in trouble, right? And that's what I want you to realize. If you take 2 minus 5, you get negative 3. If you had something like 7, which I guarantee some of you would type in and get, you got to know that your calculator or what you put into your calculator is wrong. All right. So we'll talk about these live in class just to make sure we have it. And we'll try a couple practice problems out. But for now, try those out. Give me your answer, and let's see what we come up with. Nice job.